In this class, we will study Gilbert cell mixer, and the version will be using CMOS. Its corresponding BJT version also exists. Here we are going to now study a circuit where MOS need not act like switch. If the input are sufficiently small, then we will see that they lead to output, which is product of two quantities. So first we will see differential pair as multiplier, and then we will try to modify it so that it multiplies two voltages, and finally that product is exact rather than approximate. So here we have our well-known differential pair. So these are the differential outputs. And we know that output is VO plus minus VO minus, and these individual outputs, they are VDD minus RD ID1. So this is ID1 and this is ID2 minus VDD minus RD ID2. So this will simplify to minus RD into ID1 minus ID2. So this is output. So here we see that output is proportional to difference of two drain currents. So we need to find out this difference of the drain currents, and we will see that under suitable condition for these inputs, this drain current, difference of drain current, and hence the final output will be actually product of two quantities. So we know that for mixing, we fundamentally need to multiply two entities, and those two entities are the cosine sinusoidal voltages. So now let us try to see that indeed this difference current is going to be product of two quantities under suitable conditions. We'll talk about the condition later on. So our objective is finding the difference of drain current. Now to find out this difference of drain current, we will not go into the entire detail of the derivation, but we'll write the key equations and point out how to proceed. So here there are two or three sets of equation which are going to be valid. One is for this tail current ISS and two individual drain currents. So first equation that is always valid is the sum of two individual drain currents is always equal to the tail current or the bias current. So this is one equation that is valid. Second is this voltage is VGS1. Similarly, here we have VGS2. And since the source is common for both the voltages, so difference of VGS1 and VGS2 is actually equal to difference of the two individual voltages, input voltages. So VGS1 minus VGS2 is equal to VI plus minus VI minus, which is of course the net input. So this is the second equation which we need. And the third set of equations are the equations for these drain currents themselves, which we know that is, so ID1 is equal to K into VGS1 minus VTH whole square, where we have been defining Ks 1 by 2 mu n Cox W by L. Similarly, ID2 is equal to K into VGS2 minus VTH whole square. So these are the three important equations which we need to ultimately find out this difference of the drain current. So to find this delta ID, we first need to write this ID1 and ID2 in terms of known quantities. That means ISS and the input voltage. So we have to first write these two individual equations. So what we do is first we eliminate VGS1 and VGS2 from 3A and 3B using this equation 2, and then eliminating the ID2 from equation 1. From 2, so we use 3A and 3B to eliminate VGS1 and VGS2 from 2, and that becomes the equation in terms of ID1 and ID2. So this will give equation containing ID1 and ID2. Now we eliminate, say for example, ID2 using equation 1. So this will lead to a quadratic equation in ID1. So if you solve that quadratic equation, that will give rise to ID1 as ISS by 2 plus A by 2 VI into square root of 2 ISS by K minus VI whole square. So we have already defined what is K. Similarly, we get ID2 as ISS by 2 minus K by 2 VI square root of 2 ISS by K minus VI square. Just call it this equation 4. This is equation 5. So now we have ID1 and ID2, and we have seen that the output is proportional to difference of these. So let us find delta ID, which is ID1 minus ID2. So this turns out to be K into VI into 2 ISS by K minus VI square. So here we see that output current is dependent upon not only on input Vi but also on the tail current. So in this equation, if we take Vi to be very small, very small, such that this Vi square becomes even smaller, and then this Vi square is negligible compared with the 2I SS by K term. So in that case, the above equation can be approximated as ID approximated to KVI into square root of 2 ISS by K. And this can be rewritten as 2K square root into square root of ISS into VI. So we see that final output current is product of two quantities, ISS and VI. So this is product of VI and square root of ISS. So this output is product of two quantities, VI and square root of ISS. So this circuit acts as a multiplier, of course, for very small Vi. So here, this acts as a multiplier, that is okay. But then if we want this to be a mixer, then in that case, square root of ISS should be proportional to another voltage. So if square root of ISS is function of another voltage, then we can say that mixing might take place. So we can take a pair of two differential pair and make each of their tail current depend upon another voltage. And this will be resultant circuit will be called as Gilbert cell. This is but then there will be separate ISS which will be bias current, but then intermediate ISS will become dependent upon this voltage that we are proposing. So now we will be more specific about these voltages so that we can see that they are actually the mixing of RF and LO. So we have named these inputs as VLO plus and VLO minus. So we had already seen these differential pairs and their tail current that we used here, for example, was dependent, appeared as a component in the form of square root in the expression of the difference of these two drain currents. So now we want this tail current to be dependent upon another voltage. So what we are going to do is we are going to create another pair of differential MOS like this, where now these currents, they are going to act as ISS for the above pairs, and these will be driven by RF voltage. And then ultimately we of course have final analysis. So here we are going to make this connection like this, and the outputs are going to be VO plus and VO minus. So we have these various MOS. We will label them and their currents also. So here we have M1, and this has current I1. Here we have M2, current I2. Then we have M3, M4, M5, M6, and each of these currents I3, I4, I5, I6. So these are for the individual MOS, and then their currents they combine to give rise to final currents I7 and I8, which are responsible for the outputs VO plus and VO minus. Yeah. So we see that for the pair M3 and M4, I1 is the tail current. Similarly, for 5 and 6, I2 is the tail current. So here now if we try to find the final output current, that is I difference of ID7 and ID8. So it is this difference of the current which is going to give rise to these two individual outputs. Now we see that this I7 is actually sum of this I3 and I5. Similarly, this I8 is sum of I6 and I4. So therefore, we can write them in terms of their individual currents. And now we will see that the final current, this delta ID, is going to be product of two voltages. Okay, so we have been using different symbol and more compact symbol. So let us use without D here. So now we will rearrange these currents to form difference of current for each of the pair, for this pair, for this pair. So here we will write I3 minus I4. This becomes the first pair, and then I6 minus I5. So difference of the current corresponding to positive voltage minus the current corresponding to negative voltage. So that is why we have written I6 minus I5 rather than I5 minus I6 here. So now we are going to write each of these individual difference, this one and this one. So here I3 minus I4, this is the difference of drain current for one pair. So for pair number one, let us say this is pair number two. So for pair number one, we know that the difference of current, that is I3 minus I4, this is going to be function of I1. So this thing we have already derived, and this can be written in terms of K into the input voltage multiplied by square root of 2 its tail current, which is I1 here, divided by k minus the square root of the input. So let us call this as 7a, and similarly I6 minus I5 gives rise to k VLO into 2 into its tail current, which is I2, by k minus VLO square to 7, and we will call this as 7b. So here we will do some manipulation. We will try to write I1 and I2 as perfect square, because they are ultimately appearing under square root sign. So it will be easier to do the manipulation. So we are going to take a slight diversion. And this I1 is basically the drain current for pair 3, consisting of M1 and M2. So writing the I1, which is drain current, so we had already derived this drain current. Recall that it is equal to k by 2 ISS by k plus VI into 2 ISS by k minus VI whole square. So this thing we had already derived earlier in the very beginning. Now we want to write this as a perfect square. So what we will do is we will try to convert this into form of a plus b whole square. So here we see that we have a square plus 2ab plus b square. So a into b form of factors already exist here. So we need to do the manipulation to bring about b square, and then in fact modify this b also, so that b square appears here. So for that, what we will do, we will add and subtract vi by 2, vi square by 2 rather, because in this factor we see that vi square appears. So we are doing this addition and subtraction of vi square by 2. So we can bring one of the terms with ISS by k, and we can take square root 2 common from this factor. So we get square root 2 into vi into ISS by k minus vi square by 2. So we can see that now this factor is square root of this factor, and plus vi square by 2. So this first factor can be written as square root 2 and whole square, like this. And this factor square root 2 can be modified to write as 2 into 1 by square root 2. And this can be then altered like this. So now we see that this is basically a perfect square consisting of two terms. First term is ISS by K minus VI square by 2, and second term is VI by square root 2. So we have been able to write a drain current as a perfect square. Right. So now we can write this I1, this current I1 in this perfect square form. So therefore, I1 can be written as K by 2 into square root of ISS by K minus, in this case, we have RF as input, or 2I1 by K is equal to square root of ISS by K minus VRF whole square by 2 plus VRF by square root 2 whole square. So let us call this as equation 8. So now we are going to use this in the expression for the final output. So this is delta ID, the final output current, and this is function of difference of these two current, and ultimately the function of I1 and I2. So in 7A and 7B, we will be substituting expression for I1 and I2 that we just now derived and given in equation 8. So that will give ID, which is I7 minus I8 as KVLO. So now we are going to substitute I1. So I1, in fact, we are going to substitute 2I1 by K, and what we will get is this. So this whole factor is going to be substituted using 8. So what we will get here is so this is after substituting the I1, or rather 2I1 by K. Similarly, when we substitute the 2I2 by K, we get this expression. Here. So now in this case also, let us assume that VLO is very small. So this will allow us to neglect these two VLO square terms. And once we neglect this, we can see that here we have square root, and then here we have whole square. So these two will cancel out. So we have square root here and square. So what we will get is these terms which are inside square. So delta ID now becomes KVLO into this term, say this T1 and this term T2. So this becomes basically this T1 minus T2. And in this term, you can see that the square root term is common to both. This much of term is common, so this will cancel out. And what we will survive is only this VRF term. So finally, this will become K VLO into VRF by square root 2, and of course another factor 2. So what we will get is square root 2 K VLO into VRF. This is approximate, of course, under assumption that VLO is very small. So now we can see that the output current is now product of VLO and VRF, provided VLO is small. So here we see that we get a multiplier. So this implies mixing can be done using this circuit. But here issue is that this is not exact, rather this is approximate. So now question comes that can we do something so that this product is exact, not approximate? So fortunately answer is yes, we can do something so that this product is not approximate, rather exact. Some simple modification can be done. So for that, let us see our original circuit and do modification to it. And this process is called linearization. So we revisit the differential pair that we studied in very beginning, which is this one. Right. So for this case, we had found out the difference of drain current. So this difference of drain current, this when we found was exactly equal to this expression. In this case, now we are taking LO. Here. So when we use this as a multiplier, we impose condition that LO is very small so that this term gets neglected, and then ultimately we get product of VLO and square root of ISS. So that is what we had to do to get the approximate product expression. And that existed when we converted ISS as a function of RF voltage also. So now what we want to do is that we won't have to neglect this VLO. So that is why we want to make the modification. So now let us modify this differential pair where instead of ISS, we have ISS dash, a different tail current, such that this new tail current is equal to earlier tail current plus 1 by 2 K VLO square. So suppose now this is the kind of tail current we have here. So therefore, now the difference of drain current is going to get modified to new equation. So here in place of ISS, we will write ISS dash, and ISS dash has this expression. So we are now going to arrive at this equation 2 by K. So this ISS dash will be substituted by ISS plus 1 by 2 K VLO square minus VLO whole square. So here you can see that what we are now getting is VLO into, so this term and this term, they will cancel out into 2 by K ISS square root. And this will then get simplified to 2K ISS square root into VLO. So recall that we earlier got this equation as an approximation for small LO, but now this is exact. So this is exact and no requirement of VLO to be very small. So earlier VLO was required to be very small, then only we got approximate equation. So this time we are getting exact expression. So now question arises, that is fine. Mathematically, we are able to get exact expression for the difference of this current as product of LO and square root of ISS. That is very fine. But then how to achieve this thing in real life? That means how to get this ISS kind of current. So now the next question is getting or generating ISS dash. So it is not very difficult. We can again take a pair of MOS and make this circuit out of them. And we will be calling this as ISS dash. So here we have I1, here we have I2. And we can see that ISS indeed will be of the form that we want. So I1 we know is VGS minus VTH whole square of this form, and here VGS is VLO plus. Similarly, I2 is K into VLO minus VTH whole square. So we have these two individual currents, and now we want to add them. Therefore, ISS dash as per this circuit, above circuit, is I1 plus I2. So this becomes K into VLO plus minus VTH whole square plus K into VLO minus VTH whole square. So this is ISS dash. So here we can carry out the expansion, and this will be VLO plus whole square plus VTH whole square minus 2 VLO plus VTH plus VLO minus whole square plus VTH whole square minus 2 VLO minus VTH. So this is the complete expansion. So since VLO is differential, therefore VLO plus is equal to minus VLO minus, and of course equal to VLO by 2. So we can now make this substitution in the above equation. and that will cancel out these two terms, and what we will be left is the VLO and VTH square terms. So we get K into 2 VLO plus whole square plus 2 VTH whole square. And this becomes 2 VLO by 2 whole square plus 2 VTH square, and this will finally give 2K VLO square by 4 plus VTH whole square, finally reducing to K by 2 VLO square plus 2K VTH square. So this is ISS dash. So here we can see that this is constant, and this one is what is we have been looking for. So we can say that we get K by 2 VLO square plus, let us call the second term as ISS. So we see that this simple circuit is able to generate this kind of ISS which we need, so that ultimately the difference current, delta ID rather, is product of two quantities, LO and square root of ISS. So this simple modification is able to give rise to this required equation. But here we see that ISS is dependent upon this factor K and VTH, so we actually do not have much control over ISS. So if you want some different value of ISS, it will be difficult to get that from this form of the circuit. So there is a simple modification that can be done to generate a different value of ISS. So for that, what one can do is one can go to this circuit, and here add a common voltage to all VLO inputs. Suppose we modify our circuit like this. So once we do this modification, our equations for I1 and I2, they get modified. So now in place of VGS, we have LO So this VCM gets added to LO plus. Similarly, for second VGS, what we get is VLO minus plus VCM. So now our VGS get modified because of this CM. So what will happen is now we have VCM present in these two equations. But here you can see that this VCM can be absorbed with VTH, leading to K into VLO minus my plus VCM minus VTH. So what we now get here is different TH. So we can say that this is K into VLO minus VTH dash. So we can write this in form of minus if you want, like this. So we have now a different VTH because VCM is voltage that we decide. Similarly, here also we will have K into VLO plus minus VTH dash whole square, where VTH dash is VTH minus VCM, like this. So we see that in the both the equation I1 and I2, it is VTH which gets modified. So everywhere now we will have VTH dash. So what we will get now is like this. This becomes VTH dash. So we now see that we again have constant. So now ISS is 2 into K VTH dash whole square, where VTH dash is VTH minus VCM. So using this, we can control VTH, hence we can control ISS. So modification to get a different circuit is easier. So now we would like to see that once we have this kind of modification, then what will be the output of Gilbert cell? Because in that cell also recall that we had to impose requirement of a small RF voltage to get the product of two voltages. So we will revisit the Gilbert cell. So here we have VRF plus and VRF minus, VLO plus, VLO minus, VLO plus. Here. So this was I7 and this was I8, and the output quantity was difference of these two, where we had I1 here and I2 here. So we now have delta I, which is the output quantity, I7 minus I8, and this will turn out to be I3 minus I4 minus I6 minus I5, where this is 3, this is 4, this is 5, and this is 6. So these are the various currents. So now in this case, we want to see that what will be the output if we do the linearization. So what we do is, now we do slight modification here in the circuit. And what we do is we add a new current source here, which we'll be calling as IL, and another current source here. This is also IL. So what is the purpose of these ILs? So we see that this I3 minus I4 and I6 minus I5, they are the difference current for pair 1 and pair 2 respectively. And it is in the expression for these pairs that we had the square root term and we had to neglect the LO voltage. So we know that this one is going to be given by K VLO into 2 I1 by K minus VLO square. So it is this thing which we had to take small to neglect, so we get the product of two quantities. But now we don't want to neglect this VLO, we want to keep the equations exact. So for second one, we get K VLO into 2 I2 by K minus VLO square. So this is the final output current. But this is the scenario when we have usual differential pair. That means this IL is not there. Now once we have IL, what will happen is so in presence of IL, the I1 gets modified to I1 dash, where it is I1 plus IL. Similarly, I2 becomes I2 plus IL. This is what happens in this circuit, modified circuit, right? And so therefore, this final difference current, so in place of I1, we will have I1 dash and we will have I2 dash. So therefore, delta I becomes K VLO into 2 by K. I1 dash can be substituted by I1 plus IL minus VLO square minus K VLO into 2 by K I2 plus IL minus VLO whole square. So K VLO into 2 I1, the older current, plus K plus 2 IL by K minus VLO square. So we have added this so that we can cancel out this VLO term, VLO square term, which is under the square root. And it is this term which was preventing us from getting the exact expression. So if we take this IL such that this term is equal to 0, if IL is equal to A by 2 VLO square, then the second terms, they are going to be 0. And what we will get is delta I as K VLO into square root of 2I1 by K minus KVLO into 2 square root of 2 into I2 by K. So this is what we will get when we have neutralized VLO present in the square root term, right? And now these I1 is drain current of this P3 second differential pair. So for the drain current of differential pair, we have already expressed that current in form of perfect square. So we are going to use that expression to substitute this I1 and I2. Here using equation 8. So in equation 8, we see that a drain current of a differential pair is written as perfect square of the voltages and the tail current. So this type of expression we are now going to substitute in this I1 and I2 that we have obtained, which are the drain current for pair 3. So we will now get delta I is equal to KVLO into, we now substitute 2I1 by K from equation 8, and this will become ISS by K minus VRF square by 2, this is square root, plus VRF by square root 2 . So this is the expression for 2I1 by K, and then we have whole square root. Similarly, KVLO into ISS by K minus VRF by 2 whole square, VRF by square root 2 whole square, and then finally 1 by square root 2. So here we can see that this square root will cancel this square. Similarly, this square root will cancel this square. So what we will get is basically difference of this term and this term. And here we see that the first factor is common to both, so they will cancel out each other. What will survive is the difference of the second term. So ultimately this will become exact. Keep in mind this is exact, there is no approximation involved here. So this becomes VRF by square root 2 minus minus, this becomes plus VRF by square root 2. So this finally becomes square root 2K VLO VRF. This is delta I. Now we know that therefore the output voltage VO, which is minus RD into delta I. So this becomes minus square root 2 RD VLO VRF. And keep in mind here it is exact, no approximation involved, but if changes was required in the circuit, we had to add additional tail current IL2 pair 1 and pair 2. So here we see that this does the mixing. So VLO could be say B cos omega LOT, and VRF is A cos omega RFT. So this is output. So therefore VIF in this case so is going to be here. K is also there. So therefore here conversion gain is A RD. Sorry, A and B are also there. B by square root 2. A is the amplitude of the output input RF signal.